So I'll be going through this paper first because this is a paper on very large language model from Google. So this was released first in April of last year. So it's not even 1 year since its release. And there are a lot of authors, as you see. So it was done by Google Research. And it's interesting to see actually a few notable people, especially, for instance, Jacob Devlin. He was the first author of BERT. And I'll be first talking about this paper because this will be very central to all the other three papers. So before talking about PaLM, I want to give you a brief overview of NLP in recent years. I think many of you know now ChatGPT, which was released last December 2022, and it drew a lot of attention. And I think many of you also know that ChatGPT is based on GPT-3 model, which was released in 2020, June 2020. So GPT-3 model had 175 billion parameters, which is a lot. And back then, people thought that increasing the number of parameters even more will be able to make the model even better. So this was Google's effort that went from apparently 175 billion parameters of GPT-3 to 540 billion parameters. So that's the main point of this paper. Other than that, there is no much new things. So it's basically how they could scale up the model training from, for instance, 100 billion parameters to such a large scale, which is like almost, it's more than 0.5 trillion parameters, right? And the reason why they call PaLM is that because they used new software called pathways that could link different nodes or different computers in a more efficient way. So it's more of a paper that brags about their new system that enables distributed training on their their TPU systems, TPU pods. So that's why the paper mainly talks about how the model was trained, but they briefly talk about the architectures too, but there are not many new things here, especially if you know what the transformer is. So if you go to the model part, it's very simple. They say that they actually use a standard transformer with a few modifications, which are not that many. One was that they use a different activation. It's called Swiglu. So instead of ReLU or other activations. And number two is that they say they use parallel layers. So the reason for this is that traditionally in transformer, they first compute input comes as X and they perform attention on top of that. And then they put layer norm on top of the summation of both. But then what they're saying is that, oh, we just separate layer norm part and the attention part. So now layer norm is not applied on attention part. Instead, they're just summed and then passed to NLP right away. The reason why they did this is because by doing this way, they could improve the training efficiency. Of course, they were expecting a bit of a performance degrade, but then they say that the degrade was not noticeable at 62 billion scale, and they didn't really they didn't do the experiment because it's too expensive to do this with the two configurations. But they expect that probably there isn't much quality. It's probably quality is quite the same, even if they do that in the 540 billion scale. And they do a lot of other optimization things too. So they have multi-core attention, which is basically saying that traditionally you will have different queries and key. They have different key and value vectors for all the heads, but then they found that it's actually not a bad idea to have a single key or a single value for each feature, and they just have different queries for each token. So that it's also about really making model more efficient. They use different embedding, and they use a shared input-output embedding, which means that word embeddings used in the input side is same as the word embedding in the output side. And no bias when they're doing the linear transformation, no bias. And then they also use vocab from sentence piece, which is same as the T5 model, if you know what that is. It's another older Google's pre-trained language model. And they only use the decoder part of the transformer, so decoder only setup. But other than that, they're using very much similar things from transformer. So it's another very indication that the models that people nowadays develop are not changing too much from transformer. They're changing a bit, but it's not really model centric. It's more about how they train it. So it's more about the data centric, or maybe even cloud centric, or like ML ops centric. So this is a very large model. They increased batch size from 512 to 2048, but then model is too large that even with such small batch size, they needed about 6,000 TPU chips. If you could go to the paper to see other details, but I'll just skip them. It's just the reason why I want to discuss this, that about this time, Google had the access to very large model internally called PaLM, and this was very good that basically all the research that Google has been doing since then has been largely influenced by this model. The sad part is that this model is not open source, so you cannot probably do it. You cannot test it yourself, but we know that how these models are made. Okay, so and as you see, they have a comparison with the previous models. So GPT-3 was trained with V100, which had about 21.3% flop utilization, and their new system was able to boost this to 46.2%. And they were using TPU chips V4. Okay, so now let's move to other papers, which is really more about chain of thoughts. You might have been wondering why this is related to explainable AI, XAI, but let's go to the real parts. All right, so you first noticed that this paper was actually before the PaLM paper, which was April, right? And this is January. So it is conjecture that this piece of work was in parallel with the large language model, the PaLM developments. And then when PaLM was developed, they did a few more experiments with PaLM and update the paper, which is why the paper is very recent. But you need to probably think in a way that the paper originally was not using PaLM, and then later they used PaLM and saw a lot of gains. So what is chain of thoughts? So it's very I would say simple but powerful idea. So in a standard language model, one of the fascinating features or the capability of language model is that if you give a prompt to language model, the language model tries to generate the next sentence given the prompt, which means you can give a question to the language model and we can expect language model will do some task, right? And then people were interested in using the language model to do tasks like, for instance, this like quantitative reasoning. So they have a question like, Roger has 5 tennis balls, he buys 2 more cans, and they want to get the answer, which is like 11, right? And then GPT-3 found the concept of in-context learning, which is that they have a question, but they also give the example as the prompt as well. So the prompt is including an example with the answer, and then the question, actual question, and then ask the model to generate the next likely sentence, which is probably if the model knows the pattern that the prompt has the given question, they need to answer A, then it will follow the same pattern and try to get the answer is 27. But then this answer is apparently wrong. So that's the standard prompting. And what this paper proposes that it's very simple modification that instead of just giving the answer is 11, the paper proposes to append the explanation in front of the answer. So Roger started with 5 balls, 2 cans of 3 tennis balls, each is 6 tennis balls, 5 plus 6 equal 11. So this is basically the solution, right? Not just the answer, but then how the person can arrive at the solution, arrive at the answer. And this, with simple modification, the model now is encouraged to generate the explanation first and then generate the answer, right? Because usually language model tries to follow the same pattern observed in the prompt. So that's why the model outputs now this cafeteria had 23 apples originally. This is basically about this question, new question. But then because the model generates this explanation, what they found is that the final answer becomes much more accurate. And they were using language models like PaLM to test this. So that's the idea of chain of thoughts. So there is no training done. They're just using the same language model from the PaLM paper or other papers like GPT-3. And then they just give the prompt. And if they could just engineer the prompt the way that they want, like this, then they saw that the improvement was very large. So there is a number here. So for instance, if you use PaLM here, if you just do the standard prompting, which is this prompting, right? Then you see that the accuracy is like 18% on this math word problems benchmark. And then now you see there's a prior best, which is like they do a lot of engineering to get this number. And they also tried fine-tuning GPT-3 on these problems. So as you see, this approach is able to reach really high accuracy, even compared to the prior best, which is very manually engineered model, and even better than fine-tuned GPT-3. Remember that this fine-tune means that they have the examples. It's supervised model. It's not zero shot. Whereas this chain of thoughts prompting is zero shot. So what they're saying is that zero shot is even better than, much better than fine-tuned similar size models, right? Of course, it's smaller, but it's not too small, right? So that's like very, very stunning finding in this paper. And actually, rest of the paper is trying to really analyze how this ability emerged, and also trying to rationalize, trying to persuade the readers that this is really the novel contribution, not some weird hack. So what they're so you can read this section to really go through how it works, but it's as simple as what I said. It's very simple. It's just basically by giving when they're giving the in context examples, they're actually intending they're ensuring the model will generate the explanation by giving the example with the explanation. And then they now see how the model does in the different kinds of reasoning. For instance, arithmetic reasoning, which is like math word problems, and they use these data sets. There are several data sets. These are mostly easy problems, though. It's not like super hard problems, more of a elementary or middle school problems you can think of, but there are algebraic word problems. So it's similar to what you saw here, basically, this kind of problem. And because in the in-context learning, they can give several examples, not just one. So in this paper, they choose to give 8 examples. But these examples can come from different kinds of problems. So for instance, you can choose one from math word problems. You can choose from CSQA, which is not really arithmetic, but it's more of a common sense, right? But then how they derive the answer B. So it's actually really worth taking a closer look at this. The question is that Semi wanted to go to where the people were. Where might he go? And then if you look at the answers, racetrack, populated areas, desert, apartment, roadblock. So it's actually, I'm not sure it's a good question, but well, what they're saying is that racetracks, deserts, apartments, and roadblocks don't have a lot of people, but then probably B has a lot of people, so that's why the answer is B. So the similar thing happens in the other examples too, like yes or no. Would a pair sink in the water? And the reason why the pair would not sink in the water is because the density of pair is about 0.6, which is less than water. So it's an explanation that you generate first, and then after that, the model generates the answer. So they basically just put different kinds of reasoning as a prompt, and then after all these examples are concatenated, they put a question at the last, and then try to ask the language model to generate the answer. In which case, of course, language model first generates the explanation and then generates the final answer. They use several different language models, but probably what's most known is GPT-3 and PaLM. Okay, so, and if you look at this in the how they do in the model side, that's another interesting behavior of the train of thought prompting. So one, I would say, interesting trend is that this train of thought ability does not emerge, or it's not observed when the model is too small. So this is the x-axis here is model scale. And you can think of 540 as 540 billion. So because they are all billion, right? So if you look at the these graphs across, of course, they go from 0.4 to 137 in lambda, PAM from 8 to 540. But in all the models, you will see that they're not, the difference between the chain of thought prompting and standard prompting is not large until, as you see, for instance, the size becomes large, or I would say becomes as large as 60 billion at least. So the sad part is that we'll not be able to observe this ability when the model is too small. And second part is that this ability especially is strong in this data set, which is actually harder than these two data sets. So it's not actually because this data set's easy, it's actually the other way. As you see, for instance, in this data set, the model already achieves very close to 100%. So it's relatively easy model, easy data set. But then this is, as you see, they are very near 0%. So in this case, of course, the model is, the data set is much harder. So what they're saying is that in order to get the answer, if the model needs to generate long explanation, then the chain of thought prompting works really well. But then if the data set solution or the explanation is very short, then the difference is not that high, as shown in the two bottom data sets. Okay. And in the ablation study, they were trying to see if the advantage of this train of thought prompting is coming really from what they propose, or from something else. And for instance, they thought, they were expecting, for instance, maybe some reviewers will say, oh, isn't it coming from the equation? Because that's really important part of the problem solving, right? If you could get the equation right, then you could get other things right too. But they were saying that, of course, the equation helps, but then in many tasks, it's really not that easy to translate everything into equations. So that's why the GSM-AK is really challenging. So that's what they're continuously referring to. It's a relatively challenging problem that it's not always possible to translate the entire explanation or solution into equations. So that's why it's not really worth, it's not really possible to compare in a reasonable manner. If you think about it, language is one of tools to explain things. Equation is another. So what they're saying is that in simple problems, you can explain something in pure equations, but if the problem becomes hard enough, then you cannot explain those in pure equations. You need to have the language too to explain it. So that's what they're saying here. They were also saying that maybe it's because you're generating more, which means if you're generating more, you're using the compute more. So is it coming from the more computations? But they're saying that it's not. If you just try to compute more, then it doesn't give better results. And they also say that maybe it's because that the prompt, when you give the explanation, maybe the model is able to access the relevant knowledge better. Not because the model is asked to generate the explanation, but it's just because prompt has more information. But then they were saying that if they put the explanation after the answer, so which means instead of giving example like that, they put the answer here and then put the explanation, then they saw that the performance is similar to just no chain of thought default prompting. So they were saying that, oh, it's not because of that. It's definitely because the model is trained to first generate the explanation. And they're also saying that chain of thought is very robust to the different examples given in the prompt. So you can also read this if you're interested. They're doing not just arithmetic reasoning, but also common sense reasoning. So we saw that. And in general, we see that, of course, as the scale goes up, the difference between the standard prompting and train of thought prompting becomes larger. So that's what a lot of people in NLP calls emergent ability. So what they're saying is that some certain abilities in language models only appear when the size becomes larger than certain threshold. So it doesn't get observed in a small models, but then it becomes observed in the larger models. They also do symbolic reasoning, which is like more of a synthetic task. For instance, if you're given input Amy Brown, can you get YN, which is the last letter of each word? Synthetic test, they just did it just to see how well it does, but the conclusion is the same. Okay, so I think that's it for this paper, train of thought paper. So I think if you could understand what I said for the last 15 minutes, then probably I think you will not have any problem reading this paper and understand the train of thoughts. So what they're saying is that the explanation is basically train of thought. So they're saying that the way the person thinks is usually, even if they want to answer this kind of question, they have some thoughts and then give the answer. So we just want to really try. Well, we want the language model to actually generate that thoughts that goes in the brain of the people, which can be oftentimes equivalent to explanations. Okay, so now let's move to the next paper. So this was not actually purely from Google research, but a collaboration between U of Tokyo and Google research. I think he was doing internship there, if I'm not mistaken, or maybe the other way. But anyways, it's Google and U of Tokyo. But all of this paper is basically from Google, right? So, the interesting finding here is actually can be summarized into one word or one sentence. So, if you could give this sentence, let's think by step. Where is it? Let's think step by step in the prompt. Then the model tries to generate the explanation, and it does much better than not doing it. So the difference between this paper and the train of thought paper is that train of thought paper tries to encourage the language model to generate the explanation by giving the example in the prompt as an in context, right? But then that means that you will need examples. So it is zero shot, but then still you need some examples to give to the model. But then what they found is that instead of giving those examples, they can just put the sentence at the end, and then the model also generates the explanation. And they are seeing very similar trend that the COT paper, the train of thought paper, also observed. So that what they're calling this is zero shot COT because, well, I mean, actually other things are also zero shot COT, but they still see the example in context few shot, right? So they're technically few shot COT. Then what they're saying is they can do zero shot COT really well. So what they're saying is, this is the paper. This is a COT I just showed you, right? So basically, they have question and then, this one. So this is the standard prompting, and the COT paper I just showed you was saying that, oh, you should put this explanation. Roger started with 5 balls, and if you put that, the model will try to generate this as well, and then get the answer right. And if you go zero shot, that will be just not giving this example at all. So which is just giving the question directly and then asking the model to answer, which the model gets incorrect. But what they're saying zero shot COT is instead of putting this example, they don't have example, but then they just put, let's think step by step, and then try to generate whatever comes after that. And what they're saying is the behavior is very similar to COT, the few shot COT. And that's it, actually, what the paper is trying to say. It's very simple paper, but the implication is very large. So what they're saying is they do this and then they generate something, and after that they put this into language model again and then get the answer right. And so I think the implication is simple but powerful. So what they're trying to say is here is that the language model just needs very few keywords to activate the ability to generate the explanation. And once the explanation is generated, language model is also able to get the answer correct relatively more easily. I think other parts of the paper is more of details than other things. They use some language models, but I'll just skip these things. So I'll just show you the numbers. So here we go. So as you see, these are the standard prompting, and zero shot COT is their proposed model. which is 78.7%. And they're saying that, of course, few shot COT is better than this, but then still, even zero shot COT is doing really even also as good as few shot or two shot COT. So that's the main point of this paper. I think it's of course not short paper, but I think what they're trying to say is quite simple. So they have some graph too. As you see, they have similar behavior. The model's ability to generate explanation only appears when the model becomes large enough. So they saw that in all these three models, GPT-3, this is original GPT-3. And by then, OpenAI released InstructGPT, which is basically TextDaVinci was 001, 002, these models. And then they saw that the performance gains a lot, even more in the InstructGPT than the GPT-3. And they see a similar trend in the Palm model too. Okay, so I think that's it for this paper. So that was very quick, but so I think the takeaway is really important. The takeaway is that language model indeed seems to have some ability locked inside, and the important thing is that we need to have some sort of good prompting or other ways to unlock that ability. And one of the really core abilities of language models is its ability to generate explanations. Or in more, I'll say, in other words, I really view this as a you're trying to reach the final answer, which is very difficult to reach, right? It's like a very distant answer, but then the model is trained to generate one word by one word, which is getting closer to the answer. So it's basically showing us that instead of trying to supervise the model with a very distant label or distant supervision, it's better to actually give a direct supervision every step and hoping that that direct supervision will lead to the final goal much better. And I think this is also observed in the reinforcement learning or robotics too recently, that they found that in general, we don't want to delay the reward. We also always want to supervise the model with the direct reward every time step or every action step. So that's like, I think, the general trend these days. Of course, at the end, they can fine tune this with RL, which the InstructGPT has done recently. So RL is still, I think, useful in many cases, but in the when the model is being trained early in the entire training stage, then I think the supervision is very important. So that's the conclusion of this paper. Okay, now I'm going to move to the last paper, which is 206. It's also very, I think, relatively simple, but also very big paper, I think. So now what they have done from the same company, a bit different teams, is that now the previous papers were mostly focused on how can they unlock the abilities in the language models in, well, I would say relatively in an easy way. This paper is focusing on how can you optimize language models to do reasoning as best as possible. So in that case, what they're still arguing is that they need to fine-tune the language model, and fine-tuning still is very good, very effective if you want the model to do really well on that task. Although in some cases, if you want the model to do different tasks at the same time, then maybe fine-tuning is not a good idea. But they basically, what they do here is that, okay, they now use the really large language model PaLM, and they fine-tune that on the same data sets. The point is that they fine-tune it, not prompt it, not give a prompt to generate the next sentence, but they actually fine-tune on it, and they actually find that they can do really complex questions, not just elementary school or middle school questions, but they could even do undergraduate level problems in physics, biology, and chemistry and economics. So that's really insane if you think about it, because it's very similar to, I think, what ChatGPT is showing these days too. If you ask the ChatGPT to solve some undergrad level questions, then they actually give quite good answers sometimes. So I think you can think of this as a preliminary work of ChatGPT, because this was released in the June of 2022, about 5 months before ChatGPT. So the problem is quite simple. They are given input, right? Question and target, and no question. They're given question, and the model is fine-tuned to produce the target. And of course, it might not produce exactly the same explanation and answer, but then you will see that they have a bit of different approach, but gets the same answer. So what they're saying is that it's not coming from memorization, but we think the model really learns to how to reason with these questions and explanations. So they're talking about their contribution is mostly about how they could fine-tune it and achieve very strong performance on very challenging quantitative reasoning tests, not just like these toy tasks or these like elementary school or these kids tasks. So it can be as hard as like these questions, for instance. If you think of this, you see it's not that easy, right? It's like high school or college level questions. How can you prove for every a comma b not equal to a, prove that this is it? And of course, this is a very well-known question. So if you just train on the Wikipedia, then maybe the model is able to memorize this. But then they did several experiments to ensure that the model is not really memorizing this. They are able to really generalize quite well to new questions too. So they got the question from, for instance, MIT OpenCourseWare and different places to get the training and evaluation data, even like some national math exam. So it's very challenging questions, definitely. They show, so the papers doesn't have much details because it's really about just fine-tuning language model on these data sets, and they just show different examples showing that this is really something generalizing, not just memorization. So they do some code generation too, which is also Copilot does, right? They also talk about what data they fine-tuned on, and the interesting part is that they use math web pages. So it looks like there's some website that has a lot of math. So it has about 17.5 billion tokens. But they sample some of them for their training data. It takes up 47.5% of their training data. They also use archive, which is basically the papers that we see here, all this paper that we submit. And they try to, of course, translate it into probably LaTeX and then try to create a language model on the LaTeX. And lastly, they have general natural language data. I think they did this because they probably thought they need still a world knowledge and also some general linguistic knowledge to do things, but they only use 5% of that, even though the available data is much larger. This is actually same data that the PaLM was trained on. So that's why it's present training, training. So they pre-train on this PaLM, and then they do the fine-tuning on the combination of all of these, including the same data they pre-trained on, but just a much smaller bit. And you will see, you see these numbers are quite familiar, right? So they're actually same numbers as the PaLM sizes. So they use Minerva 8 billion uses PaLM 8 billion. Minerva 540 billion uses PaLM 540 billion, but they fine-tune on this data. And they just have a different evaluation data, and then they see that generally they just do much better, right? Much better than the PaLM, for instance, prompting. So their model is always, we will think probably the best model is like this color and this color. So that's why they do a lot much better. And these are different categories. You see it now. These are not high school questions. They are more. These are not elementary school questions. They're pre-calculus, geometry, engineering, biology, and they're doing pretty well accuracy-wise. And yeah, these are like really I think very relevant to recent news that ChatGPT passed like some hard exams like law school exams, medical school exams, etc. Okay, so there are some other techniques, but I think they are relatively minor. They talk about the model mistakes too, but I think, yeah, there are some incorrect reasoning, incorrect calculations, etc. But yeah, you can take a look at that too. They also talk about false positive. It's interesting. So what they're saying is that the model has a false positive if the answer is correct, but the explanation is wrong. So it might happen more often if it's a multiple choice question, right? Because it's 20% chance to get a multiple question correct, but then it's not clear if the explanation is correct. So they try to see how much how many questions are false positives. But they saw that the trend is quite expected. So when the question difficulty is small, very easy questions, they have low false positives, but then when the question becomes harder, then they have a much larger false positives. But then on average, it's not that much. They did this through human evaluation, of course. They couldn't figure that out automatically, so they did human evaluation to figure this out. And they proved that, not proof, but then they show that their results is not coming from memorization of the training corpora. So there are several evidences. I think that's it. So I think time is almost up too. So maybe I can take a few questions if you have, and then I'll end my tutorial today. Thanks.